Hey everybody. I caught it. It's 2 hours UTC, and this is Astronomy Daily Live. You can call me Cosmic, and here we are again, once again, 2 hours UTC, talking astronomy. It's uh, it's cleared up enough here that I think I am gonna go and try observe the humanities star uh, the Humanity Star satellite. And what I'm going to do is I am going to just uh, it's it's starting to come over here at 2:13 UTC. That's 7:13 local time PM. So what I'm going to do just and this will be a first for the Astronomy Daily Live is I am going to leave the live stream running, but I'm going to go out and observe this and maybe even photograph it. Uh, yeah, so that's sort of the plan. What I'm doing right now is I am making a sign. Uh, let's see, will be no later than 2:25 UTC. This is how crazy dedicated, crazy dedicated. Well, I don't know why that's not. All right, well, whatever. Crazy dedicated I am to this dumb thing, dumb, crazy thing called astronomy. Now, this is, you know, maybe not exactly astronomy, but what I wanted to do was I wanted to try to find a little picture of humanity's star. So I can put that on the humanity star. So yeah, very likely the only opportunity that I'll get to see this. So I figure I better I better go see if I can see it. So that's exactly what I'm going to do. I'm going to just abandon post and uh, go out and do it in just a few minutes. Just a few minutes from now, I am trying to very rapidly make a little sign to alert everyone that this is happening. Insert. I did hit the insert button. Dun, 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 dun. So hope everybody's doing good tonight. As I said, it's clearing up a little bit here. I'm hoping to get back on the sky maybe tomorrow night or the night after or so. I need to do a full calibration of my um, system in order just in order to make sure that there aren't any gotchas or any surprises or anything like that. And of course, this thing is just being a royal pain. There. I will be back no later than 2:25 UTC. So yeah, that's starting for me at about 7:13. is the pass. The high point is at 7:15 p.m. and then it's gone by 7:18. So I should definitely be back no later than 2:25 UTC. What I wanted to do tonight was, you know, I was investigating um, yellow supergiant stars a little bit since um, yesterday we looked at a paper about one, an unusual one that apparently has been flung out of the small Magellanic Cloud, perhaps by like a supernova explosion, maybe 10 million years ago or so, and it has really moved quite a bit. Excuse me. So I looked up and posted a link, just a Wikipedia link to a little description of a yellow supergiant star, and these are at least according to the evolutionary models. At least according to the evolutionary models, these are these are sort of hard to see. Um, they're usually pretty massive stars, right? Um, which means they're evolving at, again, at least according to the theory, the higher the mass of the star, the faster it's burning its fuel, and therefore the faster it's evolving. And it actually goes from a blue giant star when it's very, very young to a red giant star relatively quickly. And I think it was saying like in a matter of like 1,000 years or so. So in a matter of 1,000 years, it goes from a blue giant star to a yellow giant star to a red giant star. And so being able to see uh, these yellow giant stars is actually pretty rare and pretty cool. So, I need a fill up as well. I am well, completely out. So yeah, I think I'm going to give this a couple more minutes, and then I'm going to zip outside because it is. I think it's definitely dark enough to see this thing, and I'm just going to confirm where it's going. It's going almost directly overhead. It's coming directly from the south. It's going to be going through the constellation Orion, heading north. Um, so yeah, I'm going to in just a couple of minutes here. I'm going to get up. I'm going to abandon my post, but I want you to hang with me because I will be back no later than 2:25 UTC. So you're just going to have to hang with me. This is the astronomer's life. Okay, this is part of the astronomer's life is that you have to deal with opportunities when they arise, and uh, you know, maybe in the future I can improve things so I don't necessarily have to abandon post, but I can just, take you along for the ride. But at the moment, that's exactly what I'm going to do in less than a minute here. But yes, please hang with me. As I said, I'm going to be no longer than 15 minutes, and just want to observe this interesting, I suppose you can call it, pass of the humanity star. It's going like directly overhead. Brightest magnitude is supposed to be 4.1, so it's going to be pretty tough to see, but I've got a pretty dark sky. Clouds, I don't know. I don't know. All right, I'm going to mute this and I'm going to exit for now. I'm going to I'm going to share my screen, and I'm going to go to this, and I'm going to hide that. And as I said, I will be I will be right back in 15 minutes or less. Okay. Cheers, everybody. Hang with me. Hang with me. This is astronomy at its best. Okay. Hang with me. All right, hey, I am back. That's probably the most unusual satellite pass I've ever seen. Uh, didn't exactly know what to expect, but um, I'm pretty sure I caught it on camera. Pretty sure I caught it. It was definitely not a continuous uh, bright object. What I saw was uh, periodic, just flashing, like a really fast flashing, and not periodic or anything at all. In fact, I didn't see the first flash until it was um, maybe south of Orion, and it looked the first time I saw it just south of Orion. Um, it looked sort of like an airplane, right? You know, the lights on an airplane, how they blink. I see those a lot, so it's like, okay, you know, that's an airplane, and but then um, a few seconds later, I saw another flash north of Orion, and it's like, holy shit, I think that's it. Um, and then I'm pretty sure I saw a couple more flashes. I did a series of 10-second exposures. It was moving fast, very fast. It's probably, gotta say that it's probably the fastest moving satellite I've ever seen too. Fast. So it's probably pretty low. I don't know if there's any information about that. Let's see. Uh, Maybe info here. I'm looking on Heavens Above. Um, 265 by 376 kilometers. So yeah, that's pretty low. That's pretty low. But so man, it was moving really, really fast. And as I said, I, I, it I mean, I definitely saw flashes. Very brief, like extremely fast, faster than you know, um, the iridium flares, right? Those are sort of like, you know, this was like just bang like that, and that was it. That was it. So I'm pretty sure I captured these on my phone. And in fact, if you will indulge me here, you can watch live as as I took a as I take a look at my photos that I took and see if I see it anywhere at all. I'm pretty sure I got it. Pretty sure I got it. I'm looking at the photos now, and I'm not seeing anything. Oh, I don't know. I don't know if I got it or not. The flash itself um, was pretty dim. Also, I mean, I could definitely say that it was fourth magnitude for sure. But I'm looking at these pictures, and I'm gonna have to look at these more carefully uh, later on, because I'm pretty sure that I got uh, a couple of flashes photographed. pretty sure. But if they're really, really short, like really fast, then in in the images that I have, it's just going to look like a star. And okay, I'm I know the sky pretty well. Yeah, dang, I wonder if it's there and I'm just not seeing it. There's a really good shot of Canis Major and whatever constellations are south of Orion. So, I mean, I'm definitely in the right spot. I'm just, I'm not seeing, yeah, I'm going to have to blink. I'm going to have to blink these things back and forth in order to find out. So, yeah, good. I'm glad that you're here, that you hung with me. Um, message retracted. Message retracted. I want to see what. Oh, okay. Hmm. All right. Well, cool. Well, cool. I'm glad that you allowed me to indulge a little bit there and see if I could see this, you know, moderately interesting object that was sent up there. With these eyes, I definitely saw some flashes that were right along the path. Um, but yeah, they were pretty faint, very fast flashes, very fast motion. So yeah, I'm gonna have to examine the photographs that I took carefully to see if I can see any differences. I can even do some image math and you subtract um, two images to see if there are any differences, that stand out. Because of course I didn't move, the camera. I moved the camera once as it passed overhead. I rotated, the camera north. I was looking south for most of it, and then I moved the camera, rotated it around. Uh, yeah, yeah. So yeah, pretty interesting. Pretty interesting. It's always fun, and that's one thing that you definitely don't need a telescope for at all is observing satellites, and there are hundreds of them. And um, if you're at a dark site, you can literally see dozens of them every single day. And if you're at you know if you're in a city where you really don't have uh, a dark sky, you can still see some. You can see the brighter ones, um, space station, HST, um, uh, yeah. But yeah, if you really want to be able to see all of them, or at least all the ones that are bright enough to actually see, you got to have a dark sky. But you don't need a telescope. You don't need binoculars. In fact, those would just hinder you. So, and there's a worldwide network of satellite um, um, observers who keep track of the orbits and note when the orbits have changed, and they always try to speculate on 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 why and when and how and all of that. And probably what I should do is look those guys up, um, just so I can post a link here. So yeah, yeah. So well, that was pretty exciting. As I said, I guess I was expecting to see a continuous thing, but this satellite, this humanity star, is faceted, right? It's got all these really really sharp edges. I don't know how many, quite a few, but they're flat and they're reflective. It's sort of like a disco ball, and that means that the angle between the sun, it, and the observer has to be such that you get a reflection off of one of those facets. So yeah, that was pretty interesting. Pretty interesting. As I said, I guess I was expecting a continuous thing, and yeah, the iridiums are really really cool, and you better hurry, Tom, because it's those guys are coming down, and apparently um, the new ones uh, aren't going to be reflective like that anymore. I've seen a couple iridium flares. You know, I it's cool. It's cool. Um, I don't know. I guess I don't get too excited about those things. Um, yeah, but I do like observing them. I do like seeing them for sure. It's cool. It's cool, and to know, uh, you know, what that object's situation is very very cool. When the space station goes over, you know, you can look at that thing, and it's like, man, there are people up there. There are some crazy, crazy, wild people up there. All right, what I'm going to do is I'm going to load up my YouTube channel phone. Make sure that's still running. It looks like it is. Yep, looks like it is. Mute myself over here. Just by plugging in the headphones, I can mute myself. And I guess what I'm going to do is I'm going to do an object of the day. And I think it's going to be a Messier object again. Now, Charles Messier was a French astronomer back in the 1750s, something like that. Technology back then in terms of astronomy compared to today is extremely primitive. I really, really hope that what 250, 230 years from now, somebody is saying the same thing about our technology. It's like, oh my God, can you believe what shit they were dealing with? What crappy instrumentation they were dealing with? So this is what we can say about Charles Messier. Um, was that the instrumentation that he had relative to today was you know awful. At the time, it was awesome, state of the art, I would assume. And he was a comet hunter. He discovered something like 30 some comets. Um, and when you're a comet hunter, you're looking and looking and looking and looking and looking. And he, over the course of time, he noticed all these things that to him looked like comets. Now, of course, he was looking for comets, so everything unusual is going to look like a comet, even though it might be like an open cluster of stars, which which even given the technology back then, he must have been able to resolve stars. I mean, when you look at M41, M46, M47, these are not fuzzy things. And I want to stretch and say, even back then, even given the telescopes that they had, um, I can't imagine that he saw that he was actually seeing something fuzzy. But he was a comet hunter, so he was looking for comets. It's like Percival Lowell seeing all the canals on Mars because that's what he was looking for. And so um, Charles Messier was looking for comets, and so he saw fuzzy things in the sky. But unlike comets, they did not move. So he compiled this list of these objects that weren't comets, and it's like, just don't bother with these. There's absolutely no point in observing them at all because they're not comets. And it turns out what they are galaxies, open clusters, globular clusters, planetary nebulae, and diffuse nebulae. And yeah, isn't that awesome? Isn't that very, very awesome? Um, that we now have the Messier objects. There's 110 of them, and these are really, really nice. Most of them are even binocular objects. Um, right now, M41, which is an open cluster just south of Sirius, maybe 2 fingers down at arm's length, 2 fingers, maybe 3 fingers down from Sirius, directly south of Sirius is Messier 41, and it's a beautiful open cluster. Lots of bright stars, some color for sure. So if you haven't yet, check that out. You can see it in um, binoculars. I would dare say even in the city, you should be able to see some concentration of stars. You may not be able to see all of them, um, but you're going to see some even in binoculars. If you're out at a dark site like where I am, it's pretty easy to see naked eye. So yeah, I encourage you to take a look at that. But let us choose an object of the day from the Messier list. So there's 110 of them. So I'm going to share my screen. And with the Messiers, I think I know them so well that I can claim to be like, oh, I know what that one is. But so far, I haven't done too well with that. But I'm going to try again today and see what happens here. So there's Humanity's Star. You can see how it's faceted like that. So yeah, I'm gonna have to look at the pictures and see if there's anything there. So what I do is I go to random.org and I let a random number generator choose which Messier object that we're going to look at tonight and study a little tiny bit more in detail. I'm certainly not going to dive too deep. So we're going to generate a random number between 1 and 110. Drum roll, please. M50. M50. Now, M50, as far as I know, is a globular cluster. I think it's a globular cluster, but I don't remember where. So let's go to Simbad, which is just one of the many astronomical databases. I like it. I've used it for years. It's evolved a little bit, but it has sort of the basic information about the object that you're studying, and about not only non-stellar objects like galaxies and clusters and all that, but also stars, binary stars, um, different kinds of stars, right? White dwarfs, neutron stars, O stars, M stars. Yeah. So M50. Am I right about the globular? No, it's an open cluster. Man, I'm just not doing well at all. M50. Okay. Well, I'm already seeing here that it's actually visible in my sky right now. It's not in the constellation Orion. It's just east of the constellation Orion. I don't know what's over there. Yeah, gonna have to find out. All right, so an open cluster, which is just a collection of stars. Maybe there'll be a star count in here to let us know how many stars are part of this group. It's um, it's sometimes difficult to it's sometimes difficult to figure out which stars are members of the cluster and which ones aren't. You have to, uh, you know, the best way is to look at the motion of all the stars in your field of view and see which ones are moving together. Because at least the theory goes is that all of these stars formed at the same time, sort of more or less under the same conditions. So they're all, uh, uh, yeah, you know what? Canis Minor, I think Canis Minor is too high. This is at a deck of -8, so it's below, it's south of Orion's belt. It's so yeah, maybe Canis Major. That's my guess. Canis Major, easy enough to find out. I can go to my, well, you can go to Stellarium. I can go to my charts, flip out my charts really quick, but I'm thinking it's Canis Major. Nope, it's not. It's going to be Monoceros. Yes, Monoceros. We're at 7 hours. Got to go one more chart over. Chart number 12, or Monoceros. So -8 and 7. There it is. Yeah, okay, so it's just north of Sirius. Just north of Sirius, just a little bit east of Sirius. Yep, NGC 2323. Little open cluster there. You probably already found it on Stellarium, Uncle Bill. Cool. All right. Well, let's keep going here. It looks like this cluster is moving away from us at 6.1 kilometers per second. So, you know, the galaxies that we've looked at uh, typically, are moving thousands of kilometers per second away from us. So, relatively speaking, this cluster is barely moving at all, right? Barely moving at all. It's got a visual magnitude, V, of 5.9, which makes it actually just barely visible to the naked eye. So that's sort of a collective brightness. It's sort of, they've captured the light from a large area of sky and sort of added it up, and that's what they get for that. The magnitudes of the individual stars are going to be much less. So if you're in a dark site, you may see a little tiny fuzz there. Um, pretty small, pretty small. This isn't giving a size, but it's pretty small. All right, so let's go down here and see what else we've got about it. So here's all of its other names. As I said, NGC 2323. And what's KPR and KPS? I don't know. I want to say that's Kepler, but can't possibly be, can it? So scientific papers, the references, 136 of them total, and 83 in the past 20 years. That's not too bad. Let's see, they've got a distance measurement here. 881 parsecs. So a parsec is 3.26 light years. So 881 times that is 2,872 light years away. So we go out and we look at this tonight and we're seeing it as it was 2,872 years ago. Pretty cool. Not much else about this guy. Let's see. I don't know what these plot things are. What is that? I don't know if I've ever looked at this. Taking a second to load. Okay. I don't know. I'm not too impressed with that. Looks like it's just showing the locations and the motions, maybe? I don't know. Let's look at the picture. Pictures are always awesome. Of course, it's going to be majorly blown up. It always starts that way, and you're going to zoom out. Now, Uncle Bill was saying this was heart-shaped. Hmm. Come on, you're taking more than a second here. Ah, there we go. Heart-shaped? Yeah, I don't know. There's a lot of nebulosity around. Here's some nebulosity around these stars. Some nebulosity up around this star. But yeah, that's definitely a nice little concentration of stars. Now, did Messier see just a fuzzy patch, or did he actually see, you know, maybe something funny looking that he just misinterpreted as a comet? Don't know. Don't know. I'm glad he found him though. Got his name. Got his name on him now. So this is a very rich area of the sky in terms of nebulosity. We're looking out of the galaxy along the disk of the galaxy. It's sort of on the you know uh, if you look towards Sagittarius, you're looking towards the center of the galaxy. Well, if you look to the left of Orion, you're looking out of the galaxy in the opposite way. So that's why we see all this gas and dust and whatnot, because we are actually looking in the disk of the galaxy still. We're looking through the disk of the galaxy. But yeah, there's little old M50, nice concentration of stars for sure. Um, let's there were some references there. Let's see if there's any interesting papers about this guy. Interesting interesting enough to pull up. Let's see. I'd like to see something like, okay, two massive white dwarfs. That's kind of cool. So they're seeing all kinds of different kinds of stars in this cluster, including white dwarfs, which supposedly are, very, very evolved stars, very old stars. Depletion, stellar winds, photoelectric search for peculiar stars in open clusters. So, yeah, they're looking for weird stuff inside of M50 and others. Proper motions. How good is a clock in rotation? Rotation at 13 million years. And chromatic Hubble Andromeda Treasury. Wow. Wow, I wonder what M50 has to do with M31. Don't know about that one. Investigation of the open star cluster NGC 2323 based on the proper motions and photometries of its constituent stars. Hey, now that sounds like just your basic take a look at M50 paper. So let's go over to ADS. And let's see if we can find, publish your article. Let's see how far we get here. It doesn't look like we may not get very far. We may have to buy it. Yeah, you know how annoying that is. I'm going to see. I'm going to copy and paste this into archive.org and see if it comes up. Sometimes we can get lucky. Sometimes we get lucky. NGC 2323, right? Is that, yeah. Let's just search for NGC 2323 in the title. Yeah, it doesn't look like it's on archive.org. Let's see what this abstract says. That's kind of a bummer because this looks like a sort of covers a lot, very, very specific for this object. The results of a comprehensive study of M50 are presented. The positions of stars to limited magnitude. There's some symbolism there I'm not too familiar with. In a something area centered on the cluster were measured on 6 plates. Maximum epoch difference of 60 years. The measurements were performed. Corresponding areas. Proper motions were obtained with a root mean square error of 5.85 milliarc seconds. Is that milliarc seconds? Yeah. Milliarc seconds, so thousandths of an arc second, six thousandths of an arc second. Position of the star and photometric color magnitude diagrams. The cluster was considered. Position of the object color diagram. Basically, it was established that 508 stars. 508 stars are members of NGC 2323, aka M50. These data were used to refine the physical parameters of the cluster, reddening. A measurement of reddening is a measurement of sort of how much stuff is between us and the object that we're looking at. And it looks like they've got a cluster age of 140 million years. So that's, that's pretty young, pretty young. But unfortunately, we are not going to be seeing this paper. Arg, arg. There is this one, CFHT Open Cluster Survey. So let's look at that one really quick. What? What? Oh, there we go. It had to produce it. They're calling this a rich galactic cluster, huh? I don't consider M50 a rich galactic cluster. Rich galactic cluster is like M37. So 2168 is M35. M35 is over in Gemini. That's a very, very big cluster. That also is a very, very nice um, uh, binocular scope. Cool. Thanks, Uncle Bill. Posted 4 screens. Yeah, huh. Interesting. Heart shaped. Okay. Well, let's see what they have to say about this guy. So they made observations at CFHT. That's the Canada, France, Hawaii telescope. I think that's on Mauna Kea. I want to say it's on Mauna Kea. Does it say here? Oh, it may say somewhere. Let's see. So they made their observations there. Uh, let's see. It looks like they had a three night run. 2168 was imaged on night 3. 2323 M50 during night 1. Short exposures to get the photometry of giants were acquired at a later date. See, for NGC 2323, the photometry. Let's zoom in a little bit so we can see this. The photometry from single exposures of 300, 50, 10, and 1 seconds in each color was combined to produce a catalog of magnitudes and colors. Seeing conditions, pretty good. 0.85 arc second seeing, not bad. So they looked at some standard stars in order to measure the actual brightnesses. Color magnitude diagrams. Looks like all the figures and all the pictures are at the end again. Really sucks when they do that. I understand sometimes it's easier. Using a new set of theoretical isochrones to compare the observations to theory. Okay, well, let's go to the pictures and we can sort of work backwards from there. Nice long paper. Wow. Let's see what the conclusions are. Photometry in the V&B filters has allowed us to produce the tightest main sequences to date for these clusters. So 2168 is about 1,000 stars brighter than visual magnitude 22. NGC 2323, we find 2,050 stars brighter than visual magnitude 23. 23 is a really faint. So after accounting for uncertainties in the reddening, main sequence, fitting, the distance, let's see, the distance to 2323 we find to be 1,000 parsecs, but plus or minus quite a few here. So we're talking 3,300 light years plus or minus 300 light years. So yeah, uncertainty, 10% uncertainty in the distance. That's not great, but yeah, it's something. It's something. And I think Simbad was uh, was calling it about 800 and some. Okay, so Uncle Bill says that Messier um, himself named it heart shaped. So okay, well, it was a heart shaped comet. All right, let's look at these pictures here. Let's see. Does it say where CFHT is? No, no. I want to say it's on Mauna Kea, but I can't be sure. We're gonna have to unzoom here a little bit. So these are looks like color magnitude diagrams. So along the x-axis, you can see is the B magnitude minus the V magnitude. So it it it's kind of strange, right? The Since the magnitude scale is opposite, then a B minus V means that the B value is larger, which means it's fainter. So a value of 1 here means that the V magnitude is brighter than the B magnitude. Brighter, but the B number is larger than the V number. Does that make sense? And then they plot that, the color versus the V magnitude. So you can see that it goes from, 23rd, 24th here, all the way up to maybe 8th, 9th, 10th. So lots of stars. Oh, we're looking at 2168. Let's look at M50 itself. There it is. Come on, M50. There you go. So these color magnitude diagrams just sort of allow you to start looking at populations. Mainly what we're seeing here are differences in temperature, but uh, from differences in temperature you can infer things like mass, and if the temperature and the mass, maybe you can sort of infer the age. So, there's a lot of inferences going on, but you can plug this kind of information into models and then, play with the models to see what they say. But yeah, lots of so B is quite blue. Oh, come on, screen. And V is green. I think V is around 5,500 angstroms, and B is I want to say 4,800 angstroms. Don't quote me on that. So what this is saying is that you know the the brighter stars with a V magnitude, very very bright, are a lot bluer than the faint stars, which are quite reddish, as they say. Um, so yeah, that's kind of interesting. Um, don't know what this stellarity function is. Say clearly shows a well-populated main sequence stretching from V equals 9 to V about 22 and a half. After eliminating faint blue galaxies and other image defects with a 0.5 stellarity cut. Uh, okay, so they're actually thinking that they're seeing some white dwarf stars here too. White dwarf stars are very very blue, so a B minus V of 0 for a white dwarf. Maybe. Sorry about the moving around so much. It's really annoying. Come on, machine. Not that hard. Gee whiz. Machines can drive you crazy. What other pictures do we have here? This is 2168. Let's look at 2323. So these are just model paths of evolution. Same color magnitude diagram, just showing uh, various models of stars and how they evolve over time. Kind of interesting. 2168. So let's look at 2323. Luminosity function. Um, okay. Log of n. Oh, I don't remember what n is. Oh, this is just, yeah. So this is the number of stars that have a particular luminosity. Now this is in absolute magnitude. So this is as if these stars were placed 10 parsecs away from us, what the visual magnitude would be. So you can see that, and it's called um, a luminosity function. It looks like at the top they're also showing the V magnitude as well. So that's kind of nice. So there's a relationship between the absolute magnitude, which is, as I said, the brightness of these stars as uh, if they were 10 parsecs away versus what we actually see them as. So yeah, these shapes tell us things about the characteristics of the stars. Luminosity functions of NGC 2168 and 2323 as compared to those of the solar neighborhood, the Pleiades, and NGC 2099. So let's see, which one are the Pleiades? These are the Pleiades. There's a luminosity function for the Pleiades. It looks like that. 2323 is this one, funky looking. So this is M50's luminosity function. Don't know what relative number is. This is the solar neighborhood. Each luminosity function has been normalized by the total number of stars. Okay, all right. So yeah, that's kind of an interesting way to look at it. There's all kinds of different ways of presenting data, and sometimes it's useful for the people studying it, and sometimes confusing for the people who are trying to understand what they're talking about. uh, Mass function. Okay, I'm not going to get into this. It looks like we're running over the hour a little bit, so yeah, maybe we'll get into this. But yeah, it looks like they did a pretty heavy study of M50 and M35. Well, they're looking at the white dwarfs there. Summary of published cluster parameters. Reddening, age, references, star counts. So yeah, they're seeing you know four stars that are between 9th and 10th magnitude, and 260 stars between 22nd and 23rd magnitude. So if you add all those up, you get however many they said. That's got to be at least 1,000. Geometry of annuli. Okay, I think I know what that means. I'm not going to get into it though now. Let's see. Let's see what else they have to say about this guy. Distance from the sun, 912 parsecs. So somewhere around 100 and some million years old. Diameter, 10.6 parsecs. Number of stars, they're saying about 1,500. Cool. Cool. Summary result. Oh, I was looking at the wrong one. This is the right one. Age 102 million years. Lunar diameter 8.72 parsecs. So it's small, pretty small. 3,200 stars though. Pretty awesome. Pretty awesome. All right. I think that is just about enough fun for this evening. I'm glad you all could be here for M50. Thank you for indulging me in running out and seeing if I could see Humanity's Star, the satellite. I'm going to take a look at the pictures that I took and see if I can identify it. I'm pretty sure I got it. I'm pretty sure I got it, but I didn't know what I was looking for. So yeah, we will see. In the meantime, I think it's time for me to get back up to the ship. Glad you could come here. If you're new to the channel, just hopping on now, hit that subscribe button, hit the like, hit the don't like, whichever you prefer. I like to see and read comments. Um, Make sure to share this as well. I want to spread the word. I want the circle to get larger and larger so we can have some interesting conversations. Um, I don't recall ever hearing uh, M50 being called the heart-shaped um, cluster. So that's very, very cool. That's that's new. I'm going to have to investigate that a little bit more. At least according to Messier, it looked heart-shaped to him. So I'm going to have to check that out a little bit more. That's very cool. Lots of stars in that cluster, like 3,500 stars. So that's a lot of stars. That is a very, very rich cluster. Looks like they're seeing maybe some white dwarfs in there too. So awesome, very awesome. All right, I'm gonna let you all go. I definitely respect your time. Glad you could come in. Don't want to take up too much more, but we're talking astronomy, so it usually goes over a little bit because that's what we can do. Astronomy is so awesome. We could talk about it. I could all day and all night, and I basically do, except thinking about it instead. Made some pretty good progress with characterizing my telescope back there. Um, Shot out a couple more plots similar to yesterday's, just showing um, that the astrometry looks really, really good. I'm definitely doing sub arc second um, 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 accuracy and um, precision on that. Photometry is a little rougher. I'm getting about a tenth of a magnitude accuracy at best, plus or minus about a third of a magnitude. So I'm hoping to improve that once I can actually calibrate the data. I'm using raw data right off the telescope, and the rule is garbage in, garbage out. So I know that what I'm giving photometry is pretty garbagey. So I don't have a lot of high expectations for being accurate and precise with the photographic with the photometric measurements at this point. Once I'm able to calibrate the data, get rid of the dark current, make sure it's flat, get rid of all the bad um, pixels, either ones that are extremely bright or extremely faint. Um, I'm hoping that the photometry numbers kind of tighten up a little bit. I would like to see less than a tenth of an arc second accuracy and less than a tenth of a magnitude um, um, precision on both of those. So that's sort of what I'm aiming for. I think I can. I think I can. We'll see. We'll see. Also depends on how on the algorithm used to make the measurement as well. So I'm probably going to have to fine tune that a little bit too. It's a little bit rough and clunky at the moment, but that'll fix itself. I've done it before. I just have to write the code again to do it. So, all right, I am definitely going to get out of here for now. Thanks for coming in. I will see you on the spin and take care.